So, I accidentally hit the power button while I was recording. Took me a few minutes before I realized that it stopped recording. I kind of finished this example. And then it was like, oh, I'm done. And I was like, oh, shit. It has been recorded. But luckily, it recorded the first 35 minutes or so. Here's the rest of it. Also, having the little extra time, I can explain the KLY equivalent a little bit more. I took a little bit of time, looked at it mathematically, came up with a better way of saying what it's doing. Okay, so we're right in the middle of this example, right? Almost done with the example, actually. We looked at the KL, right, in the weak axis, and the KL in the strong axis. And so we have to check both of them because this one is a bigger unsupported length, but also stronger capacity, bigger R as well. This one over here, right, shorter unsupported length, right? Or shorter, shorter unsupported length, and weaker because it's the weak axis buckling. Okay, and so what we do is we have to start for the weak. We have to start with the weak axis first. Okay. And that's what we're going to do, design for weak axis first. And we enter this table with 900 kips and 13 feet. So we come down, I just happen to have the right page here. So this is, it was asked for the lightest W12 section that would work. So you go to the table that has W12s in it, right? And we look for 13 feet, that's our unsupported length, right? And then we read across until we get the capacity that we need. And our PU is 900 kips, so we have to find PU that has PPN, a capacity that has at least 900 kips. Okay, so here's 13 feet, right? We read this sucker across. Let me highlight this, 13 feet. We read it across, right? And we're looking for one of these things that have at least 900 kips. Okay, and so the 954, 862 would not work, 954 would work. So this would be a W12 by 87 is what this thing would say we would use. W12 by 87 with a PPN of 954. Okay, and so we come up here and we say, yep, this results in W12 by 87. Okay. And this gives us a phi PN of equal to 954 kips. Okay, and so that is the design for the weak axis. Okay, for the weak axis, it would say you need a W12 by 87. Now, the next part, so that we're not done yet, right? Because we have to check this 26 footer, right? And so what we need to do is come up with the. What happened? What we have to do is come up with a member here that's going to work. Or sorry, we have to come up with a KLY equivalent. And so we need RX over RY. So what we would do is we'd go for a W12 by 87 and look up RX over RY. One place you could do that is in the dimension tab. You go to the dimension tab, you look up RX, you look up RY, you take one divided by the other. But this brings up a good point. AISC is no dummy, okay? And so what they've done is down at the bottom for each one of these members, right? So these are all different members. Down at the bottom, they have provided to us RX over RY numbers. Would you look at that, right? Very smart individuals, okay? The AISC. And so what we do down here for a W12 by 87, RX over RY is 1.75, okay? The other thing to note here is that, right, so what if we end up designing for a slightly different member, right? Because we don't know which one's going to control. But RX over RY is pretty dang constant on each one of these pages. There's variation between pages, but on a certain page, they're pretty dang close to each other. Okay. So let's come down here, W12 by 87. So RX over RY is 1.75. So now we calculate, so now we'll do strong axis. Okay, we look at strong axis here, and we look at KLY equivalent, right, is equal to KL divided by RX over RY, KLX even. Okay, KLX we found to be 26 feet. Okay, and then we divide by that by 1.75. So what you get here is 14.86 feet. Okay, so my KL for the strong axis is 14.86. At this point, I can compare this directly to the y-axis, right? KLY is 13 feet. KLY equivalent is 14.86 feet. So this tells us that this controls the design, right? The largest KL controls. Okay, that guy's going to control the 14.86 feet. So now at this point, I have to design this for the strong axis buckling. So I need to go into that table. And I'm looking for 14.86 feet and a PU of 900 kips. Okay, so we come down to the same table, probably be on the same page or close to it. Instead of looking up 13 feet for my span, it's going to be right around 15 feet. Okay, is that right? We'll go over that final exam study guide later. 14.86 feet. Yep, so close to 15. And so then we look up 900 kips. We're looking for 900 kips. And what we selected before was a W12 by 87. Right? And that's that guy right there. So our FPN for a W12 by 87 is 896. We need 900 kips. This will probably work, right? Because this is for 15 feet. If we did, you're allowed to do linear interpolation. If we did linear interpolation between 15 and 14 feet, this would go up to at least 900. So I would be comfortable saying that that thing is, that guy's going to work. And so in this case, it is the other direction that controls, but it happens to be that it stays the same, okay? And so W12 by 87. FPN at 15 feet is equal to 896 kips. Okay, right? So this would be okay, right? And you could do a quick linear interpolation to make sure. Or, right, if you just want to be careful, because your job and people's lives depend on it, just grab the next one, which would be a 12 by 96. Which would give us FPN is equal to 990. Okay, that too would be okay, right? And so where did I get that? Well, that would be just the next number over for 15 feet. Okay, FPN is equal to 990. It would be equal to 990 for a W12 by 96. Okay, so your homework takes it a step further and it says, okay, what if you were to increase the load, okay, for this particular member, okay, what failure mechanism would control, okay? I think the homework problem specifically asked that. And so keep in mind, right, this is our capacity, again, looks something like this, right? And it goes, actually it's more for columns, it's doing this, right? And the key is going to be looking at what the KL over R is, right? If this is, what is this, 4.71 times the square root of Fy over E, I think. Let me just double check. And that's that border, right? Or E over Fy, rather. I had it backwards there, okay? It's this number right here. K over Y, is it greater than 4.71 or is it less than 4.71 times E over Fy? So let me correct that down below here. All right, E over Fy. Okay, what I need to do is I need to calculate what KL over R is, okay, and check if it's less than or equal to 4.71 square root of E over Fy. Okay, that's what you do. And in this case, what you would check would be In this particular case, it would be in the X direction, right? But if it's the weak axis that it's controlling, you would check your KL over Y and check to see if it's less than 4.71 times square root of FOC. If it's less than this, okay, if KL over, in this particular case, it's the X that controls. If it's, right, because it's the, right here we said that this controls design, so it's going to be the X. You calculate that and see if you're less than this. And what's it's saying is you're probably down here someplace. If you were to increase the load, okay, so if I was less than 4.71 E over Fy, I would hit, in this particular case, inelastic buckling or yielding first. If my KL over R was greater than 4.71 E and I increased my load, okay, I would hit this, which would be my elastic buckling, okay? So when the problem statement asks, like, what failure mechanism controls, what span controls, okay, that's what you're checking for. So in this case, it would say that the 26-foot span in the strong axis controls, okay, and you know, I didn't do this, but you would check the KL over R and see if it's less than 4.71 square root of F. If it is, then it's this that controls. If it's greater, then it's the elastic buckling that controls. And so that kind of finishes that off. Okay, you have a homework problem very similar to doing this, except for you have different. It just doesn't look like this. It's more complicated. That's part of it. Import that. Okay, this is what your homework is going to be. Okay, so this is the case where you have side sway, but you have no rotation. Okay, this you have a pin support that's only in the y-axis, so it's on this pin is only supporting weak axis buckling, right? And this guy right here, we have another pin support that is supporting the weak axis at this location, but then it's also supporting the strong axis at this location too. So this is basically showing that these guys exist going into and out of the board as well. So it's supporting the strong axis as well. And then at the bottom, in both directions, you have a fixed condition. And then this condition exists at the top. So then to do this problem, I would kind of I would look at the strong axis and encapsulate all these, right? This one go from here to here with a certain K, and then it'll go from here to here with a different K and a different L. And then the weak axis, it's going to go from here to here, here to here, and here to here, all with different lengths and Ks, okay? And usually what I do is I write all those things over here first, come up with the weak axis one that controls, the one with the largest K, L in the weak axis, and then come over and then come up with an Rx over Ry and compare it to the x-axis as well, and then do the design that way, okay, and see how it goes. And then here's if the axial load was to increase, what failure mechanism would control, okay? And then not only that, I'd like to see which span is going to control, which span is going to control, and if it's going to be strong or weak axis, okay? Okay, so then real quick, last thing. I came up with a better way to explain it. Okay, this is what I was fumbling around with earlier. So this is what I came up with. It took a couple minutes and came up with a better solution here. Okay, so when you do this KLY equivalent thing, what we're doing is that we are pretending that KL is smaller so that the table for weak axis buckling will give us the capacity for strong axis buckling. We're just manipulating the table in order to give us the capacity that we would have gotten in the strong axis had there been a strong axis table in existence, but there is not. And so we just trick the table into giving us the strong axis buckling capacity by pretending that the KL is smaller. Mathematically, right, this is if we were just looking at elastic buckling, which we're not, there's more to it, but if we were looking at just elastic buckling, this is the equation for elastic buckling. That table is based off of this. So what we're doing is we're taking this KL and we're divided by Rx over Ry, right? And so that Rx over Ry comes down to the bottom, KL divided by Rx over Ry. There it is. This Y and this Y cancel out. And we've turned this into the strong axis buckling equation. We just take this equation, we divide the KL by Rx over Ry, and it gives us the strong axis buckling capacity. That's all we're doing. Okay. I don't know why I had so much trouble thinking of that earlier. Okay. So there's a better explanation of that. All right. That is that. Last lecture, okay, I'm going to do an exam review on Oh, probably Friday, and it'll be interactive between us and you, and maybe even the week after. I'll see when most people can meet. We're are right now. I have us taking the exam that final week during finals. Probably make it a take-home exam as well. Probably due on that Thursday of finals week. But hope everybody's doing well and keep up with this. I think this homework will go pretty quickly.